Several new ROS users find it difficult in the beginning to differentiate between a ROS workspace and a ROS package, and also may find difficulties in understanding how to set up their first ROS projects. In this video, I'm going to explain the process of creating a new workspace and a new package so after installing ROS, we need to do a little bit of configurations to enable ROS in Ubuntu operating system. So ROS will be installed in the directory opt ROS and then the name of the version. In this case, it's Kinetic, and here we can find the whole workspace for the ROS installation. So the workspace represents the working area, and any workspace would have a special file that is called setup. Okay, so we have setup.bash and setup.sh for different type of shells, and this file must be executed to enable the workspace. So the workspace is actually the working area that contains the file that we need to run ROS or ROS applications. So we need, for example, to run the setup.bash using the command source. So instead of writing this manually every time in a terminal, we should write it into the .bashrc, which is a file automatically executed whenever you start a new terminal. So the .bashrc contains several script commands that will be automatically executed every time you open a terminal. So in the home directory, we can type gedit.bashrc, and then we will have this file open. And then I'm going to write the command source/opt/ros/kinetic. This is the path to the workspace, and this is the file setup.bash that will be executed to enable the workspace. So here, if I type roscore before opening a new terminal, before the changes take effect, you will see roscore is not detected. Okay, same thing if I run roscd, that takes me to the default workspace. Okay, it cannot be executed. Now, if I close this terminal and open another one, so the changes will be effective, and then I can make roscd. It will take me to the default workspace. So this is now the default workspace, and also roscore, which starts the main node, is going to be working. However, when working with ROS, it is not convenient to work in the default workspace. The common practice is to create your own workspace where to put your ROS projects so that your ROS code and programs will be in a workspace different from the default one. And for this, we need to create our own workspace. So let's see how it works. So let me first go to the home directory. So this is our home directory. And basically, we need to follow the instructions in the ROS tutorials, create a workspace for Catkin. In a nutshell, Catkin is just the compilation framework used by the ROS environment. To create a Catkin workspace, so it means the workspace where we are going to set up our projects and put our files, we're going first to create a new directory in the home folder, and the common practice is to put it in the home folder and give it a name, Catkin WS or Catkin workspace. You can give it any name of your choice, but this is the common name in ROS. And then we will create also the src folder, which is going to be the folder that will contain the source file of your code. It will contain the ROS packages that we will create later on. So first of all, workspace, let's say this is a big area. You can consider it as like a big table where later on you're going to organize your projects, which we are going to call them packages, into this workspace. So we can say that a workspace is a complete working environment, and packages will be your own individual projects that will be put inside the workspace. So let's create the directory, and now we can go to the directory Catkin workspace, and finally we can compile the workspace using the command catkin make, and now the workspace is created. So after compilation, we have now created the Catkin workspace into the home directory, which contains also a build, a development, and a source folder. So you can see now, if we make roscd, which is the command that takes you to the default workspace, it is going to take us still to the default workspace /opt/ros kinetic. Even if I close and open again, so you can see the new workspace is still not enabled. In order to enable the workspace, we must also source the setup.bash that is located in this workspace, and we can find it into the devel folder. So here we have setup.bash. This one must be sourced to enable this workspace to be the default one. So how to do this permanently? We go to gedit.bash rc, and we need also to do a source home/riot_u. This is the name of the user. And so now this is the home directory. This is our Catkin workspace that we have created. And this is the devel folder. And finally, we execute the setup.bash. Okay. So now I enable this instruction. And now I will open a new terminal. So you can see now, if I make roscd, it's going to take us by default to the Catkin workspace that we have created right now. Why? Because this one was sourced after the default one. So you can see now, if I go back to gedit.bash rc, I am printing the ROS package path, which is shown here. This is now the default one, and this is the workspace of the installation. Now that you have created your workspace, it is time to start creating your ROS projects. So a ROS project is actually called a package, and a package is defined inside a workspace as a location where to create the files and the programs of the ROS project. So first of all, we need to go to the Catkin workspace, and as you already know, the Catkin workspace contains 3 folders: one for the build that contains the compiled files, one for the development, and one called SRC for the source files. So our packages or projects will be created into the SRC folder. So let me go to the SRC, and then in order to create a new package, we need to use the command catkin create pkg, and then we specify the name of the package. In this case, I'm going to call it ROS Basics Tutorials. And finally, we need to specify the dependencies, which means the ROS libraries on which the project will depend. Of course, there are common libraries that we can include in the project since the creation time, like for example, standard messages, ROS.py for Python, and ROS.cpp for C++. We can include also other libraries, but at the creation time, we may not be able to know what are all the libraries that our project will depend on. So this is not a problem, because later on, when I will explain how to create new ROS applications and programs, I will also explain on how to add manually new dependencies into the project. So for now, it will be okay to just create the project with only these 3 dependencies. So now I will execute the command, and the new ROS package is created, but still I need to compile the workspace to complete the creation of the ROS package. So to compile the new package, we need to go to the Catkin workspace directory, and then we use the command catkin make. So now our project is created, and we can go to the SRC folder, and we can check that we have already ROS Basics Tutorials created. Okay, this is Catkin workspace, this is SRC. And inside we have an SRC folder, and this is where to put the source code of the ROS programs that we will develop, and include here the place where to put libraries. For the moment, our source folder is empty, and we are able to create new programs here. So now we can use an integrated development environment to open this project. For example, I'm going to use Visual Studio Code, and you can use any other of your choice. Remember that you can refer to the video which IDE to choose if you want to have more information about the different possibilities available to develop ROS programs with different integrated development environments. So we can open Visual Studio Code, and then you can drag and drop the folder here. So we have here the source folder. And then we can create new files. Let me create, for example, talker.cpp. Listener listener.cpp. So just for illustration purposes, this is a sample code for listener.cpp. And this is another code for talker.cpp. Of course, I'm going to explain more in details the Talker listener application in a later video, but just to show you how to create nodes and how to execute them after creating your workspace and your package. The next step is to add the compilation information into the Katkeen workspace. So I will add an executable for the Talker and an executable for the listener. Of course, this concept will be explained in the complete details in the lecture of how to implement a publisher and subscriber. So here, when we add the executable, we must make sure to specify the correct path to the node. So here, this is the path to the node Talker, is src talker.cpp. So we go to Katkeen workspace, src, ROS basic tutorial. So this is now the src file, the CMake list. So we have talker.cpp. And same thing here, src listener.cpp. After that, we can go to the Katkeen workspace and finally execute the command Katkeen make. So now our two executable files are created and we can run the program. So first of all, we run the ROS core. Then using Ctrl-Shift-T, we open a new terminal. We can run ROS run. So the name of the package that we have created, which is ROS basics tutorial. And then we have two nodes. So let's start with the Talker. Okay, the Talker now is publishing. And in the second terminal, we run the listener program, which is also in the ROS basics tutorials package. And then we press listener ROS node. And we can see now hello world 11, 12. So you can see now 13. You can find 13 and so on. So this is a publisher is publishing and this is a subscriber. So as I already mentioned, I'm going to explain more details how the publisher subscriber works. It is just a matter of demonstrating on how to create an application right away after creating a workspace and a ROS package. So if you did everything well so far, in principle, you should have the following. You should have your Katkeen workspace. And here you have the build, the devel, and the src folder. And inside the src folder, you will have the ROS Essential CPP that you have cloned when you have installed ROS Noetic. And also you have the ROS Basic Tutorials. This is the new package that we have just created for illustration purposes, and it contains the listener.cpp and talker.cpp. This is kind of the basics, the most basic package that you can create in ROS. So in the next lecture, we're not going really to work more in ROS Basics tutorials, but basically all the code that you will need in this course is found here. Okay, you have src and you have topic. This is the basic here. You can find also the same talker and listener node already here in C++ and in Python. And of course, I'm going to explain in detail all these different applications in the next lectures. Okay, so just to help you more, I'm going to put this Katkeen workspace as a resource into this lecture, so you can download it and verify that you have the same thing as I have done so far. And also another thing to check is in the .bash rc file, make sure that you have sourced the installation folder of ROS and also your Katkeen workspace. If you have everything done like this, so you are in the right path. And now we are going to move further to discuss more the ROS concepts. During this course, I will be demonstrating several programs and examples. To make things simple and easy for you, I will show you how you can easily get all the code and the program files that I will be explaining during this course. So first, I assume that you have already created your ROS workspace and you are ready to create the ROS project that contains the programs of this course. So let's get started. So as already explained before, the ROS project files will be located into our workspace. So I assume that you have a Catkin workspace. So here I have a fresh Catkin workspace. So what we will do, we open a terminal, okay, to make sure that our workspace is activated by default. So this is the case, you can write ROS CD and it should take you to the Catkin workspace here. Then we go to the source folder, and here where we are going to add our packages. So for the moment I don't have any package here. You may have your own packages, so you can add this one in addition. This is possible, or you can have also a fresh workspace like I'm having here now. So we will get the package from my Git Hub account. My Git Hub repository is located in this URL, github.com/anisgoubar. So you can here, and then you go to the different repositories, and then you select ROS Essentials CPP. There are two different options to get the code. The simplest one would be to download the zip file and then open it. One thing you need to do is to remove the word master, because this represents the branch, so we don't need to have it in the name of the folder. And then copy this folder, and then you can take it into the source folder of your Catkin workspace, like here. And now we have all the files here. However, I do not recommend this approach, although it's going to work fine. But there is another way, so I'm going to delete this one. And the other way is to use terminal command with the Git command line. So first of all, you must make sure that you have Git installed on your computer. If you don't, you can install it easily using sudo apt get install, and then you install Git. So I have it already installed on my computer. Then, in order to get the package, we go to the src folder again, and now it is empty, as you can see. You can click on this link to make a copy of this URL here, and then using the command line git clone, and then copy the link over here. So now it's going to clone. It means making a copy of the files into your workspace. So you can see now it has been copied again. If I do ls, I will find it over here. So this approach is better because later on, if for example I will make some changes to the repository, you just need to pull again the changes without the need to download the whole package again. And in any case, either the first approach or the second approach would work pretty much fine to get the good program files that you will need in this course. So after that, you need to check that the ROS package that you have downloaded compiles and works fine. In this case, you go to the Catkin workspace directory and then write catkin make compile. So if everything works fine, you will have a correct compilation, as it is the case on my computer here. Okay, and now if you go to the build directory, you will find that the binaries now are located in this directory, and also you have a folder here, ROS Essentials, in the devel share directory. And finally, you can open Visual Studio Code. And as usual, you drag a project directory into Visual Studio Code, and you will have all the files. So the files will be located here into the src folder. So you can see here you have the src folder, and you have two folders: topic 1 basics, topic 2 motion. So basically here, all the tutorials related to publisher, subscriber, service, and action lib in ROS are located in topic 1. And the tutorials related to the Turtle Sim cleaning application and motion are in topic 2 folder. You can open any of the files from here. And also, you can enable the integrated terminal so that you can execute your ROS commands from here, or also you can execute them from an external terminal. So you can run from here or run from here. So here, for example, I can run, let me run ROS core on this external terminal. And here I'm going to run the Torcol application using ROS run, the name of the package, ROS essential, and then Torcol node. Now it's working. So this was an overview on how you can get the code and open it using Visual Studio Code. In the next lecture, I'm going to provide a detailed explanation of the code presented in this ROS package. The objective of today's lecture is to talk about the ROS computation graph. So what is the ROS computation graph? Is basically the following chart. ROS basically is composed of different nodes, which we call the ROS nodes. So imagine that you have a node here, and the node is a C++ code or maybe a Python program. It can be a C++ program or Python program. And every node in a ROS computation graph can communicate with other nodes. And there are different ways of communication. So the most fundamental way of communication is the publisher-subscriber mode. And we have one publisher that is sending messages to a subscriber through a particular topic. And today we are going to see in detail how the messages are sent between a publisher and subscriber, and how even to write a Python program and C++ program to publish a message from a ROS node to another ROS node. The second type of communication is what we call ROS services. And here you have you can implement a server in, for example, in node 1 and a client in node 2, and then the client and server can exchange messages. And in this case, the client has to send requests, service requests, and the server is going to respond back with the service response. And the third type of communication in a ROS computation graph is what we call the action leap. Okay? And it's similar to a server. So the difference between ROS service and ROS action leap is that here the server is synchronous. It means when the client sends a message, it will have to wait until the server sends back a response. However, in the action leap communication mode is completely asynchronous. What does it mean? So the client can send, for example, a particular objective or particular goal to the server. And while the server is executing this goal or this objective, the client can do any other thing in parallel. And in the meanwhile, the action server can send back feedback to the client. For example, I have completed 25% of the task or 50% of the task and so on. Okay? Until the complete task is completed, and finally the action server is going to send the action result to the action client. So basically these are the three communication modes, and you will learn all of them during this course. Today I'm going to start with the publisher-subscriber communication between two nodes, and then with the server and action leap as well. And of course, as already mentioned in the previous lecture, that we have a central node that is called the ROS master, through which all the communication will happen between two different nodes. So let's see a particular example of a ROS computation graph. Here we have, for example, we have our robot, which is our Turtle Sim robot. And the first node that we have to start in the ROS computation graph is ROS core. So this is the first node that we have to start. And then you can start a subscriber. For example, you can start the Turtle Sim node, which is your robot. In this case, it's a simulated robot. So what it will do, it's going to announce itself to the ROS master that it is a robot, and it is called Turtle Sim. It can receive messages, for example, of topic CMDVAL, Turtle1 CMDVAL, and specifies also the message type. We will see this in more details. Okay, and in the same time, you can have another node which teleoperate the robot. Okay, it will also contact the ROS core, the ROS master, and it will publish messages on the same topic. Okay, CMDVAL topic here. And finally, the ROS core is going to inform the subscriber, we have a new publisher that will send you messages. And finally, the communication can happen between the publisher and the subscriber. This is the most basic example in a ROS computation graph. Okay, so let's see now the details. Now, the first thing that you need to do when you start working with ROS is to start the ROS core. Okay, you have ROS core. You started, and you will have an output similar to this one. Of course, there is a lot of text here, but maybe we can focus on the most important parameters. So, for example, here you can see what is the ROS distribution. So here, for example, this ROS score corresponds to the Noetic version, which is the latest version as of now, as of today. And also it provides you some more information about the ROS master URI. So here it means it's the ROS server is running in localhost on the following port. This is the port number. So you can think about ROS as a network, but network inside the local machine. Okay, now after finishing with the start of the ROS score, we can identify a certain number of nodes. So let's look here at the command ROS node list. It's a command that will allow you to find the list of nodes that are currently running inside a ROS ecosystem. Of course, since we have only started the ROS core, so the only node that is available now is the ROS out. Okay, we have only ROS out, which corresponds to this node, which is the ROS core, and the ROS master, which is currently running. Okay, so ROS node list, it provides you the list of all nodes in a ROS computation graph. You can also find the list of all topics using the command ROS topic list. Okay, and here we have only 2 topics, again related to the ROS core. Now let's try to run a new node, because the ROS core is a very special node which allows to run the whole network. But now I want to run my robot. I want to run my application. So basically the common way to run any application in ROS is to use the following command. Okay, let's try to understand this command in detail. Okay, so the first part in the command is basically the ROS command itself, and here it is ROS run. And ROS run, it's the ROS command to run any node. If you want to run any node, if you want to execute any node, whatever it is in C++ or in Python, you need to use the command ROS run. And then the second step is to provide the package name. So TurtleSeam here, it's the ROS package where the ROS node that you want to execute is located. So what does it mean, this ROS package? Where it is located, actually? So remember, when you have installed ROS, it was installed in the repository opt/ros/noetic. We have /lib and then /turtleseam. Inside this folder, we have an executable node that is called TurtleSeam. So this TurtleSeam here, this is the name of the package. Okay, so we should have some package in the ROS ecosystem that is called TurtleSeam, and inside of which we have the TurtleSeam node. And this is the script, or this is the code that we want to execute. It can be a C++ code, or it can be a Python code, the ROS node to execute. And the ROS node also should be located in the package that we have called just after the ROS run command. So here we are going to execute the TurtleSeam node that is located in the TurtleSeam package using the command ROS run. So this is the command to run any package. If you have another node in another package, you just type ROS run, the package name, and then the node name. So by executing this command, you will have something like this, which is the TurtleSeam robot. Okay, so this is the output of the following command. And here you can see it's starting TurtleSeam node. It gives you the name of the node, and just waiting for any action. So now you have a robot that is waiting for certain command to be executed. So what we can do with the robot usually, we can make the robot move. This is like the most basic operation that we might need from a robot, is to make it move. So we need another node in the ROS computation graph that is responsible of making the robot moving. Okay? But before even going to the node to make the robot move, let's observe what happens after we execute the command ROS run TurtleSeam node. Okay, so here we have executed this command. And now we can observe, if we run ROS node list here, we have a new node. Okay, so this new node corresponds to the TurtleSeam node, oh sorry, this one, the TurtleSeam node that is created. Okay, using the ROS node list. And if we run also the ROS topic list to check the list of topics, we will discover that we have 3 new topics that are related to this robot. So one of the topics is this one, the CMD val, okay, that the robot is going to use to receive velocity command. Okay, it will receive velocity command through this topic. Okay, so we have here the turtle sim is associated to this node here, and we have 3 new topics. Now let's run another node. As I already mentioned to you, we need to have another node to make the robot move like here. So for this, we are going to use the teleop node. Okay, so we have the teleop node. We can run it, run turtle sim teleop node here. And the teleop node is used basically to make the robot move. If you add the turtle sim teleop node, you can make again the ROS node list, and you will find that now we have 2 nodes instead of 1, or 3 nodes, sorry. You have turtle sim node, which is this one, and you have teleop node, which is this one. Okay, same thing if you do now ROS topic list again. We don't have new topics. Why we don't have new topics? Because the teleop turtle is using the same topic, this one, the CMD val. Okay, so this CMD val is published by teleop turtle and is subscribed by the node turtle sim. Okay, so we don't have new topics, but here we have a new node. When we started this node, we have a new node here that is called the turtle sim. Okay, now coming back to our to this figure. So what is this node here? We have this keyboard represent the TurtleBot teleop key. This turtle sim simulator corresponds to this one. Okay, and now we have a topic that is called Turtle1 CMD val, okay, which is used to send velocity messages from the keyboard script to the robot node, or from the keyboard node to the robot node. Okay, so if you want to make communication in the publisher-subscriber mode, you need to define one publisher, one subscriber. You need to define a common topic. Let's say this is like the communication channel between the 2 nodes, and you can send messages according to this topic. So this topic will send data, and this data will have some kind of message structure. Okay, message structure of the data. And the subscriber of this topic is the turtle sim. So the information is even consistent with this. If you make the information of the turtle sim node, it will tell you that it is subscribed to the CMD val. If you make the information of the CMD val itself, it will tell you that the node turtle sim is subscribed to the topic. Okay. So this is now the relation between the topic, the node, and how the communication is going to happen between 2 different nodes in ROS. Now, after understanding the relation between the nodes and the topics, let's focus more on the message structure. If we take the whole scenario in a very abstract way, we have a teleop node, that is the keyboard, and we have the turtle node, that is our robot, and there is a communication, a unidirectional communication from the teleop node to the turtle node through the topic Turtle1 CMD val. But now the question, okay, what kind of data this topic is going to carry out? So it turns out that the data here of CMD val has the following type. It has a type we call twist message. It has 2 components, linear component and angular component. And for linear we have X, Y, Z, and for angular we have X, Y, Z. So why we have the following message structure? Why this structure of the message represent a motion? Because in 3-dimensional space, usually we have 3 coordinates. We have X, Y, and Z. And same thing, we have X and Y and Z for angular, to rotate. So we have 3 coordinates for linear motion and 3 coordinates for angular motion. Let me illustrate this through an example or through this chart. In 3-dimensional space, you have 3 axes. You have the X-axis, you have the Y-axis, and you have the Z-axis. And you can have motion in any of the 3 axes. You can have motion along the X-axis, you can have motion along the Y-axis, and you can have motion along the Z-axis. So this is why the linear motion here is expressed as X, Y, and Z, because we can have speed we can have speeds in the different direction of the 3D coordinate space. In the same way, we can also have rotation around the x-axis, or a rotation around the z-axis, or a rotation around the y-axis. Okay, so for example, the rotation around the y-axis is called the pitch, around the x-axis is called the roll, and around the z-axis is called the yaw. Okay, so I hope now we can understand well why we have three coordinates in the linear direction and in the angular direction. Okay, so now let's look at the type of the message itself. This message that is composed of linear motion and angular motion has a particular type that is called in ROS geometry MSGS / twist. Okay, what does it mean this? Usually any message in ROS, it is represented by two names. So the first name is the ROS package, where the ROS message is located. And the second name is the ROS message name itself. Okay, so here, when you see this following message, you know that the twist message is located in a package called geometry MSGS message. And that's true. If you go, for example, to /opt /ROS /noetic /share /geometry MSGS /MSG folder, you will find a file that is called twist.msg. Okay, and twist.msg, it represents the following message. And this is why we call this message as geometry_MSGS, which is the package name here, and /twist, which is the name of the file containing the message. So what is the content of this message? The message has two fields of type vector3, the linear and angular. Okay, and vector3 is another message also located in geometry MSGS. It has three components of type float, x, y, z. So basically any position in space is represented as a double of type float 64. Okay, and here we have two components, one that is for linear motion of type vector3, so that's why it will have x, y, and z. And the second one is angular for rotations, and also it has x, y, z values. Okay, so this is the structure of a ROS message. What you have to keep in mind that the ROS message is expressed by the package name and also the name of the message. Okay, the package name is the folder where the message is located, and the message name is the name of the file where the message is located. We're going to see by the end of the lecture how we can create our own custom message. So the twist message is already predefined in ROS. It is a standard message defined in ROS. So when you install ROS, you will have automatically the twist message. You will have several other messages that will come with the ROS installation. But still, ROS offers you the possibility to also create your own custom message. Okay, and this is why we have, to represent a motion, we have a linear motion with x, y, z, and angular motion with x, y, z. So I hope now that you understood well the relation between node, topic, and message. Now, if you want to see the content of a message, also there is a very simple command in ROS. Okay, it's called ROS MSG. So ROS MSG, it's the command for dealing with messages. And the second command is show. So you write ROS MSG show, and then you give the message that you want to show. So here, it will show you the content of the geometry MSGS /twist. If you use this command, we are going to make a demo just in a while, just providing the concept now. Then I'm going to show you all of this through a real demo using ROS. Okay, so now if you execute ROS MSG show geometry MSGS /twist, you're going to find the linear component with x, y, z, and the angular component with x, y, and z. Okay, and you can do this for any kind of message. Any message that is already implemented in ROS, you can use ROS MSG show geometry MSGS /twist, or the name of the message. It can be, for example, standard MSGS /string, or geometry MSGS /vector3, or any message that you want to see its content. This is another example. For example, I want to see what is the content of the pose message. I can use ROS MSG show geometry MSGS /pose. And here we can find that the pose message, it has also two components, but different from the previous ones. it has a position component and orientation, because the position in space is represented by a point, x, y, z in space, and also the orientation. Okay, orientation around the x-axis, y-axis, and z-axis. But here you can see that the orientation is represented by some kind of weird type that is called quaternion, and it has 4 values. Okay, we will keep this later when we talk about transformations and navigation and so on. I will explain why orientations are expressed in quaternions. But orientations, they have, just in a nutshell, they have different ways of representation. They can be represented as rotation around the x-axis, y-axis, and z-axis. But basically, in robotics, the standard way to represent orientation is the quaternion representation. And I will keep this to provide more details later. So now we have understood what is a node, what is a topic, what is a publisher, what is a subscriber, and how a node is able to send a message from to another one. Now the question is, how can I publish a message on a topic? We have used the TurtleSeam teleop, which is already implemented. It sends velocity commands. But if you want to send velocity commands, there are different ways. You can do that using a command line. You can open a terminal and just type the following command: ROS topic, and here the command will be pub for publishing. So -r, it means repeat this 10 times. And then you have to provide the topic name. I'm going to publish on this topic a message of the following type: geometry MSGS twist, and then the last line will represent the data itself in JSON format. Okay, so if you want to publish any message on a topic, you can use ROS topic pub. You provide the topic name. In this case, I'm going to publish turtle1/cmdvel, and you have to specify the message type, and then you specify the data. So what this will do is going to make the robot move in the x direction, okay, with a velocity 0.1, and all other velocities will be put to 0. So this is what this command is going to do, and it will repeat this 10 times. If you make -r 10, it means it will repeat the command 10 times, and finally it will stop automatically. Okay, so another nice utility that you can use in ROS is the ROS RQT graph. Okay, you can use ROS run RQT graph, and what it will do, it will plot you the following graph showing all the ROS computation graph. Okay, so here in this graph, what do we have? We have 2 nodes, teleop turtle and TurtleSeam, and we have they communicate between each other using the topic turtle1/cmdvel. So it will provide you kind of a nice summary of your whole ROS ecosystem, all the nodes that are running and which topic they are communicating through. Okay, using ROS run RQT graph. Okay, now let's try to illustrate this through some examples. I'm going now to start a new ROS session. So what is the first thing we need to do? Okay, we use ROS core. Okay, that's fine. So now we have our ROS core running. And let me open another terminal. And now I can run ROS run TurtleSeam turtle underscore or TurtleSeam node. Yes, you can use TurtleSeam node here. So now I have my robot. This is my robot here. And I can run now a third terminal. So which node I have to execute to make the robot move? ROS run, and then the package name is TurtleSeam, and then the node name. What is the node name? Is turtle underscore teleop key. Okay, and look now, I can press any key, any arrow to make the robot move. Okay, so let's make ROS node list now. We have 2 nodes. We have the turtlebot teleop, the teleop turtle, and TurtleSeam. Okay, we can also make ROS topic list. So we have the 2 topics of the ROS master, and you have also 3 topics related to the Turtle 1, Turtle C. You have CMD-val, you have pose, and color sensor. Let's see a few more operations that we can do now. So for example, we can use the command rostopic echo slash, and I would like to see what kind of messages are sent through the CMD-val topic. Okay, so rostopic echo, Turtle1, CMD-val. Look, now when I try to make the robot move, okay, every message that is published is going to be captured by this command. So you can use rostopic echo. Okay, so rostopic list is going to give you the list. You have rostopic info to get the information about a particular topic. And you have rostopic echo that will give you the content of the message when it is published. Okay, so topic, list, and echo. You can write rostopic. Look, you can write here rostopic, and then double tap. You will see all the different operations available for the rostopic command. You have rostopic echo, you have rostopic find, you have hertz, you have bandwidth, you have info, you have list, you have pub, and you have type. Okay, so now we have here the linear velocity and the angular velocity. Let's try to look at the message content. So if we make rosnode list, and then rosnode info, and let's take, for example, the following one for the teleop turtle. Okay, so this is the information about the teleop turtle. It does not subscribe to anything, and it publishes on the message on the topic Turtle1 CMD-val. What is the type of the message? It's called geometry MSGS twist. Okay, so what is the command now that I need to use in order to check the content of the message? Yes, we can make ROS MSG now, because we will use ROS MSG and then show, and then the twist message. Look now, it's the same thing that we have seen in the slides. Geometry MSGS / vector3. This is the type of the linear component, and this is also the same type for the angular component. And here we have x, y, z values, and here we have x, y, and z values. We can do the same, for example, for the message vector3. Okay, look, the message vector3 is composed of x, y, and z, same as here. Let me see what is the type of this message. Okay, so I'm going to use rostopic info to check the type of the message first. It is turtle scene pose. So now I have the following one. I can use ROS MSG show, and I want to show the fields. So, okay, this message presents the pose of the robot in 2-dimensional space. This turtle scene is going to operate only in 2-dimensional space, and in the 2-dimensional space we have x and y. So you have here x. This is the x-axis, and this is the y-axis like this. Okay, and you have theta, that is the orientation. Look now, I can make the robot, for example, rotate. Okay, so here the orientation is going to change, and here the x and y position is going to change. We can see this. And you have the linear velocity, that is the speed, and in the linear direction, and the angular velocity, this is the speed of rotation. So now let's look at the content of the message when it is published. We can use rostopic echo Turtle1, and then pause. Look now. So now it will tell me that the robot is located in the coordinate 8 here, and y with an orientation 0.73 radian. Now let's try to move the robot. For example, I'm going to move the robot to... Okay, so what is the position of the robot here? Look, it's 0, 0. Okay, so it means this point is the point 0, 0, is the origin. And for example, if you move, you can see now, for example, it is in the coordinate 5 in the x direction, and the coordinate 2 in the... So here we have, this is 5.1. Okay, in the x direction, this is the x direction, and this is the y direction here. and you have a position of 1.94. Okay, so this topic allows you to find in real time the pose of the robot. Okay, and the pose of the robot is published by the robot. In contrast to the CMD-val, it is subscribed by the robot. This position is published because it represents a state of the robot. Okay, also the orientation here. The orientation here is represented in radian, not in degree, by the way. Okay, so let's try to move the robot, for example. Okay, so you can see the orientation and the XY coordinate will change accordingly. What is the advantage of using ROS? So at any time, it gives you, as a user, the possibility to send commands to make your robot move. And also, it will give you, as a developer, the ability to read the state of the robot at any time. So in this particular context, the state of the robot is just the position, but it can be anything else. It can be, for example, you can collect from the robot maybe an image from the camera sensor, or, for example, the location of an obstacle from a laser scanner, or any other thing. Okay, so using ROS, you will easily get any information that you want from the robot, and you can easily send any kind of command to the robot that you want to monitor, to control. Okay, so this is the objective of ROS, is to make communication between different nodes and different processes inside the robot, okay, to develop any particular application. Okay, let's now also try the command that I already showed to you. Let me remove this. So if we want to use ROS topic pub, we can use ROS topic pub -r, for example, 5 times. So what I have to provide now, slash, I have to provide the name of the topic. So I'm going to publish a message on the topic Turtle1 CMD val. And what is the type of the message? Is geometry underscore MSGS twist. And then I have to specify the message itself. Maybe it's a little bit long, so I'm going just to copy this one. Okay, let me copy it here, and let's see what's going to happen. Okay, do you see that the robot is moving very slowly? Okay, so it's now publishing messages to the robot. I can change, for example, the angular velocity at the same time. So maybe I can put this 0.5, and let me put this minus, for example, 0.9. Look what's going to happen. It will make a combined motion. Okay, why it moves backward? Because here the velocity is negative. Okay, and here it's rotating into the counterclockwise. Okay, look, it's rotating in the counterclockwise. So this is a circular motion. It's making a circular motion in the backward direction and counterclockwise. So imagine that now I can change this command. Okay, let's make this, for example, -0.5, and this one +0.9. Look, now it's going clockwise and in the forward direction. Okay, so you can see the impact of the sign on the motion of the robot. Okay, now if I want to make the robot only rotate, what I should do here? What the command I have to put? Rotate in place. Not as a circle, but just in place. Yeah, we can put x equal to 0. Yes. And yeah, whatever. Yes, look. Look now, -0.5 is rotating counter or clockwise. Clockwise. If you want to make the robot move straight, what we do? Yes. And we can put x, for example, any number. 0.3. Okay. Okay, did you understand now? Yeah, okay, that's a good question. Why we didn't put over the Y? We can try over the Y. It's not going to move because, for example, if you have a car, can it move in the Y direction? The steering doesn't allow the car to move in the Y direction. Okay? So same thing for the robots. Usually this is called the holonomic robot. Holonomic robot, it moves a robot that can move in any direction. And there are some particular wheels, like the Swedish wheels, that allows the robot to move in any direction. But for normal robots, like with differential drive or Ackermann steering, like for example the case of the vehicle, they can even move either move in the X direction or rotate around the Z axis. So this is the axis for which they can move forward, and this is the axis around which they can rotate. Okay. Now, for example, if you take the case of an airplane usually, or a drone or something like this, it can rotate over the three axes and also move around the three axes because it will move in the three-dimensional space. But usually for ground robots, they move in two-dimensional space. We usually send commands over the X-axis in the linear component and the Z-axis of the angular component. How the publisher get the information from the ROS? Yeah, it's the ROS master. Yeah, now, yeah, when you start the ROS master, you are establishing a network with different nodes. And these different nodes can communicate between each other through a particular topic. Okay, so here, this node, that is the turtle seam teleop, it communicates with the node, that is the turtle seam node, through the same topic. What is the topic that they communicate through? Is the topic turtle1 CMD1. Okay, yes. The publisher, this one. Yeah, of course, this means that there is a C program or a Python program that it will detect which key was pressed and then will create a publisher. So now just in the next slides, I'm going to show you how to create a publisher using a C++ program or a Python program. Okay, yes. Which one? See, yeah, CMD-val, yes. Yes. Yeah, you can publish through this topic through a Python or C++ program. We are going to show how to do this. Now I'm just introduce you the main concept. Try to understand when I say ROS node, you understand what it is. When I say ROS topic, you understand what it is. When I say a ROS message, you understand what it is. But later on, I'm going to show you what are the capabilities that ROS offer to you as a software developer to develop this kind of application from using Python or C++ programs. Okay. So now we are still in the step of understanding the fundamental concept of ROS computation graph. And now later on, we are going to see how we can develop programs, okay, that make different nodes communicate between each other. Okay. Okay, so I already mentioned to you that we can use the ROS computation graph using ROS run RQT graph. Okay, and here you will see that we have our teleop turtle, we have turtle seam node, and we have the topic turtle1/CMD1. Okay, so yeah, this is the same now if you do here, if you do ROS node list. Okay, you have turtle seam, which is this node. This is just a graphical representation of the ROS computation graph. Instead of making ROS node list or ROS topic list, you can just do it through this graphical interface.